So in this bimolecular mechanism, why it is called bimolecular mechanism? Because this is the step in which this transition state is formed. That step is very slow, and because it is slow, this is the rate determining step. So because it is rate determining step, and in this rate determining step, both nucleophile as well as this substrate, right, both are responsible to determining the rate of reaction. That's why it is called bimolecular reaction. In chemical kinetics, we have already seen that if two molecules are involved in rate determining step in a reaction, that is called a bimolecular reaction. So that's why this is bimolecular reaction. And we have also seen that after reaction, the product is, there is no difference in product in the two, that is whether it is SN1 or whether it is SN2, the product is same, that is halogen is removed and nucleophile is attached to the carbon. The thing is, if you see this from the side, the nucleophile attacks from the side where the halogen was already there. So that's why in the final product, there is no change in orientation as well. So we say that this retained its configuration. But in SN2, as you can see here, nucleophile attacks from the opposite side of the halogen, right? And that's why the product which is formed, that is of just opposite orientation or configuration. That's why we say that there is an inversion of configuration involved in this type of reactions. So these are the salient features of bimolecular reaction. So the last one is that it involves inversion of configuration. And our next topic, next discussion is actually based on this, that how this inversion happens, what is it called, what all other points are there which we have to study. So those things we will see now. So before that, let us see some more detailed and one more thing we have seen here is that SN2, whether it is SN2 or SN1, there is another factor which governs it, and that is called steric hindrance. And what is that? That is nothing but, as you can see here, when this nucleophile is attacking from the opposite direction of what? Of halogen. So this is our halogen and this is our nucleophile. So nucleophile is attacking from the opposite direction. So when it does that, obviously here there are three substitutes. You have to imagine this in 3D. So in 3D, whenever we draw this on paper to represent this 3D, out of this, you can see that there are three circles here, 1, 2, and 3. Out of these, one will be in the plane of the paper, one will be above the plane of the paper, and one will be to the back side of the plane of paper or the screen. So that's how this 3D. So you can, as I said earlier, you can imagine it as a stand of tripod, the three stands of a tripod. So these three stands of the tripod are not in the same plane. Out of these, we may have two in one plane and one in other plane. So they will be aligned in 3D. Now that's why to represent that in 3D, we use this representation. The one which is in the paper, we write it like this: straight line, just a line, right? So that means that bond is actually in the plane of paper. Okay, the one which is on top of the paper, that is, suppose if you are seeing your screen, so you can imagine that as the bond which is coming out from that carbon towards you. So that we will represent like this, like a wedge. Right? So this means that, or this is to represent the bond which is coming from the paper, from the carbon, say carbon is on the paper, and from that paper or that screen, this bond is coming towards you. So suppose this bond is made with hydrogen. So the hydrogen, this hydrogen is in the plane of paper, this hydrogen is coming towards you. And there will be the next one, the third one, which will be actually on the back side of the screen. So the one which is on the back side of the screen, we are going to show that by dashed lines. Right? So this means that this hydrogen is actually on the back side of the paper. So this is how we represent it in 3D. Right? So just remember this representation. This is very important. Okay, now, so that was the most of the things we have already discussed about the SN2 mechanism. In SN1 mechanism, the reactions are generally carried out in a polar protic solvents such as water. Let's move to the next one, that is unimolecular. That is SN1 reaction. So this is SN1 because it is 1 represents unimolecular. And this is carried out generally in polar protic solvents. Polar protic solvents. If you remember, the halogen has to come out from the original molecule and form an ion. So that's why the medium which we need is polar protic medium. So examples of such medium are, say, H2O or ROH. So such are, and even RCOH, that is acids. Now the reaction between, if you want to see the example for this, suppose if I have this C in 2D, if I'm writing like this, so there are 3 methyl groups attached, right? And there is a Br here, that is bromine. Now reaction, this is obviously tertiary, and there are 4 carbons, so tertiary butyl bromide. Now when I write this tertiary butyl bromide, that means I am writing the common name. It is not the IUPAC name, because if, as per IUPAC, it has only, the main chain has only 2 carbons, and the 2 carbons are substitutes. So that name will be different. So that will be actually ethane, but right now we are writing butyl. Right? So as per IUPAC, it will be 2 bromo, 2 methyl propane, 2 bromo, 2 methyl propane. Right? So this is first carbon, this is second carbon, and this is third carbon. So it has 2 bromo, 2 propyl, 2 bromo, 2 methyl propane, or yes, that is the name of this compound. Now when this reacts with, when this compound reacts in this medium, that is OH negative is part of the medium. So when you have that, there is a reaction between this bromide and the OH ion, and that will actually give us the final product, that is this. The bromide goes and there is this OH is attached here and bromide ion is released. Now when we analyze this, we see that it actually follows the first order kinetics. So here it's not second order reaction, this is actually a first order reaction. How do we know that? That is, I think in chemical kinetics class we have seen that we will analyze the data. Data will be what? Data will be nothing but for a given amount of time, what is the amount of reactant left, we observe that, or what is the amount of reactant consumed, we observe that, we note that, and then we try to find out which order reaction is this. So here we find out that this is a first order reaction. So if it is a first order reaction, that means the rate of the reaction depends upon the concentration of only one item, right? And this is the thing on which rate of reaction will depend. So rate of reaction depends on only this, right? And we can say that the rate, right, will be equals to some K constant into concentration of this CH3 price Br concentration. So that means it is actually a reaction which is dependent on only concentration of only one, but there are two reactants involved. That means that this is a multi-step reaction. So there will be more than one substeps of this reaction. In the first step, the tertiary butyl bromide undergoes ionization to produce a carbocation. So the step one, let's see what happens in that. The tertiary butyl which we had, that is C, I'll just write Me. Me is for methyl, right? To save time, I'm writing like this. And this is connected with a bromine. So what happens here is that in this first step, it actually gives us a carbocation. So that is carbocation like this, plus sign on this carbocation, and this methyl group, and methyl group. And there will be this bromide ion. This is the first step, and this is ionization. So from neutral, you are moving to ionized form. So this is a slow step. Right? And in the second step, whatever nucleophile we had, that is step 2, the nucleophile which we had will attack this carbocation. Carbocation is positively charged carbon. So that is the site on which a nucleophile can attack easily. So it is OH negative. So that's why this negative site or sign attacks this positive site. So this is a nucleophile, and nucleophile is attacking your carbocation. That's why this is called nucleophilic substitution reaction. Now this step is going to be fast, and what we will get ultimately we'll get the same thing which we was earlier. Only thing is the Br will be replaced with this OH. So that is the two-step process, and yeah, first one, ionization, is the slow, and it is obviously fast one. So in this, what do we see here? Here there are two reactants, but here there is only one reactant. So it depends only on that. That's why this is called unimolecular reaction. Right. So as we have already discussed in previous class as well, that both the reactions will happen in both the compounds. That is, I mean, in all the compounds, whenever you see this nucleophilic substitution reaction, this both the mechanisms takes place. It's not like only one of them will take place, but which route they will favor, that is very well defined. So how it is defined? So we have already seen that there is the steric hindrance comes into picture. So if you have, say, just C H H and H and some halogen here, or you have C H CH3 H, or and the last one is the tertiary compound. Now if we talk about SN2 and SN1, both, so both will be there observed, but one of the routes will be favored. So which one will be favored, that we'll see now. So in this, suppose the attacking reagent is some nucleophile which has to attack. In SN1, that nucleophile will be attacking from the opposite, and in SN2 that will actually opposing entering from the opposite direction of this halogen, right? And what about SN1? In SN1 it will be approaching from the this nucleophile will be approaching from this side. This is the difference. So now we see that when it does, it will be easy to do here. That is from this, from the opposite side of halogen. That is for SN2, it will be easy to do in the first one. But in the second one, there is one methyl group. In the second one, there are two methyl groups. And in the third one, there are three methyl groups. So now, if the nucleophile comes from this direction, that is, if the nucleophile comes here, so it will have more steric hindrance or more steric effect or hindrance, same thing. So that means what? The favor of, or as you move like from here to here, steric hindrance increases. And because steric hindrance increases, we say that SN2 reactivity decreases, right? So SN2 reactivity decreases. That mechanism decreases. It doesn't mean that reaction won't take place. The mechanism, the conditions favoring that mechanism are not there. So that's why that mechanism won't be favored, right? And what happens about SN1? Obviously, if SN2 decreases, that means in this SN1 will be favored. or SN1 reactivity increases. So in general, 3-degree carbocation will favor SN1 and will, you can say, it will not favor SN2, right? So that is the reactivity order. So one we have already seen earlier, that is based on the halides, that which one will be easy for out of these four, right? This we have already seen, this part, that iodide will be easy to ionize. So that's why that will be favoring the nucleophilic substitution reaction more than bromide, then chloride, and then chloride. So that was something which we have already seen earlier. And this is the next reactivity order, that is, but here it's not straightforward. It is based on SN2 and SN1. Now, due to this greater stabilization of allyl and benzyl carbocation due to resonance, so even the primary allylic and primary benzylic halide show higher reactivity in SN1 reaction than other simple primary halides. The allylic and benzyl carbocation. Allylic carbocation is nothing but where you have a double bond attached to the carbocation. So what does that mean? That means this CH2 double bond CH single bond CH2 plus. So it is a carbocation, but this carbocation carbon is actually, the positively charged carbon is attached to a carbon which is having a double bond with a carbon. Such carbocations are called allylic carbocation. This is called allyl carbocation. And we know that there is concept, and this you must have seen, that this is equal to this ABC, and on C there is a positive, A double bond B single bond C, and on C there is a positive charge. That means there will be resonance involved here. Resonance involved here means what? Delocalization of pi orbitals. So due to that, it will have two resonating structures. The second resonating structure will be this, that is, now the positive charge will come here, this bond goes CH, and there is a double bond here with CH2, right? Now if you see, these two structures are exactly same. These are equivalent structures, equivalent resonating structures. I hope you understood why equivalent. There is a double bond between CH2 and CH in both the sides, and after CH there is a CH2, and that CH2 has plus charge on both the sides. So that's why these structures are same. Only thing is their orientation is different. Such structures are called equivalent resonating structures, and that causes more stability or gives more stability to that particular carbocation. So this causes more stability, right? And next, so that was about allyl. Now next we see benzylic halide. So benzylic means what? Benzylic is this, a benzene ring, and on that benzene ring there is a methyl group attached, and hydrogen is removed from that methyl group. So that means there will be a positive charge here. And now if we observe this, this is A, double bond B, single bond C, and on C there is a positive charge. So due to the same reason, now this is also responsible, or sorry, capable of doing or showing resonance. So now there will be resonance effect here as well, and it will be the same thing. That is, the flow will be same. That is, from double bond it will come to this because it has a positive charge here. So electron movement, the pi orbitals delocalization, which you will be showing, that will be shown from electron rich bonds wherever there are double bonds or electron rich area to the electron deficient region. So that's what we are doing here. So now when this happens, the second structure which will be formed here, right, will be something like this. And this we should know to draw it fast without making any mistakes. Remember, while drawing any resonating structures, the atoms don't change. When atoms change their place, that is actually called hyperconjugation. So atoms won't change their place. So you can draw at least this thing fast. That is, without any thinking, you just start drawing the atoms at their own place. Right. Now, the area which is right now undergoing delocalization is this. So we will have changes there. Other things will remain as it is. So draw that fast. That is this and this. And now whatever changes will be there, only that changes we have to show here. So what all changes will be here? Because this bond has moved from here, so on that carbon which is marked here as A, there we will have a positive charge. It is same as we have seen here. There is no difference. And there will be a double bond with CH2. Now again there is A, double bond B, and positive charge on C. So again this is responsible for, or this is a candidate for resonance, right? So again, if we have to draw this fast and correct, draw the structure as it is. So there won't be any change in the structure, right? And the delocalization is going to happen here in this region. So apart from that, everything else will remain same. So that means there will be a double bond here as well. There will be double bond here, and that's all. Now the delocalization you have to show, that is there is double bond here and a positive charge there, so it will move like this. So if this happens, double bond is moved from here to here. So double bond has moved there, but positive charge has come here. And now again there is A, double bond B and C, and on C there is a positive charge. So again draw the structure for this. Right. So now this structure and this structure is going to remain same. There will be some movement of electrons here to be shown. It will move like this. So again this double bond position will change from here to here, and there will be a positive charge here. Okay. Right. So this is the thing. And now next, again you can see there is A, double bond B, single bond C, and on C there is a positive charge. So now if we have to show this movement of electrons, we'll show from here to here. So the final, how do we know final? That we'll see. So this is the structure. This will remain as it is. This here, it is involved in the delocalization. So this bond is gone, and because it is gone, the positive charge will come here, and there will be a double bond here. So these are the resonating structures, and you can see that there are 1, 2, 3, 4, 5. There are 5 resonating structures. So that means again, this also gives more stability. So here you can see that these are bulky groups. The carbocation which is formed is itself a bulky molecule, but there is more stability in this. That is, when the reaction goes through this formation of carbocation, it undergoes a state of more stability. And because there is more stability in this, that is in formation of carbocation, right? And how this carbocation is formed? So there must have been some, say, Br attached here, or here some Br attached with this carbon. So that Br, when that Br goes, when this Br goes, there will be a positive charge here. When this Br goes, there will be a positive charge. Right. So the answer is why. The question is why this Br will go. Why won't the nucleophile will attack from the opposite direction? Answer is yes, it can attack. But now we are seeing whether that will be more preferred or this approach of ionization will be more preferred. So that's what we are discussing here. So when in such cases when ionization happens, in such cases when ionization happens, after ionization we see that there is formation of a carbocation, and we see that they have this structure, they have this sequence, that is a double bond B single bond C, and on C there is a positive charge. Due to that, it will show resonance, or we can say that that carbocation is stabilized or gains more stability due to resonance. And because it gains more stability, that's why this route or this path will be preferred over the SN2 mechanism. Right? So we conclude that the methyl and primary alkyl halides, that is the first case, and this methyl and primary which we have seen here. This is methyl and this is primary. This is secondary and this is tertiary. So the methyl and primary alkyl halides predominantly undergo substitution reaction by bimolecular mechanism, that is SN2. So here majority will be SN2. But in all other cases, that is tertiary, undergoes right. So that is what we have to understand, or that is the conclusion for this. That is primary and the methyl and primary alkyl halides will predominantly undergo substitution by SN2 mechanism. The tertiary alkyl halide undergoes substitution by SN1 mechanism. The secondary, which we saw here, which is here, right? This secondary which lies in between primary and this is the secondary, right? Which is between primary and tertiary. The primary allylic and primary benzylic halides, which we have seen below. Primary allylic and primary benzylic halides may react predominantly either by SN1 or SN2 mechanism or by both the mechanisms without much preference, depending upon the nature of the nucleophile and the solvent. So this relative reactivity of haloalkanes is an important point of this chapter. So as we have already discussed, the reactivity of haloalkanes is due to polarity of carbon halogen bond. obviously the first thing which we see is that greater the polarity, more reactive should be the haloalkane. So, and that is there. The reactivity of haloalkanes should, I mean, in that case, should decrease in order that is chlorine, fluorine, bromine, and iodine. But we have already seen that it is actually opposite of that. Iodide is more reactive. So Ci bond is the easiest to break because of bond dissociation energy which is involved with that. Bond dissociation energy is nothing but the energy required to dissociate or to break a bond. So that energy is less in case of iodide and more in case of fluoride. So that's why the reactivity of iodide is more. So that's about the stability or factors or the reactivity factors or reactivity orders of SN1 and SN2. In our next class, we will be discussing the isomerisms or the optical isomers, which are very important for this topic. So we'll see what is optical isomers. If you have your old books, you can go through that once, what is optical isomers and all, and that will make the things easy for us. So it will be again a very big topic. So we need one whole class for that. So that we'll do in the next class. That is the optical isomerisms. Anyone, any doubt in today's class?
So when will be the next class?
Next class will be tomorrow. I mean, today the next class is there, but that is for physics, I guess, at 5 o'clock. So for organic chemistry, I think you will see in that schedule when is the next class. Most probably it will be tomorrow. Okay then. So we'll meet again at 5 for physics.